So yes, so a phase diagram in general, matter has three states, so solid, liquids and gases, and that's what we want to describe. At what temperature and pressure, which phase would be more stable, right? Or which phase would exist. So normally the things, kind of things that you see are something like this, and if we think that we are at, actually this should come all the way to some place, right? I think we are at high temperatures, low pressures, then it's most likely that we are in the gaseous phase, right? So this particular region would define the gas. If we are at low temperatures, right, so random motions are less, right, if things get a chance to attract to each other, and we are at higher pressures, we can compress things, then we end up with the solid phase. And the third one left is, of course, the liquid. There are some things which you already know at the phase diagram. The one over here, let me use this color, that's called the critical temperature. Critical temperature, TC. So there's no distinction between a liquid and a gas beyond this. Okay. There's no boundary. So normally, if you think of some boiling process, right, and if you boil something in a beaker, maybe put a lid on top of it, and let's say the vapors are colored, then you can see some vapors, you can see the liquid. Right? There's a distinct boundary over there. But if you are in the supercritical regime, which means beyond this regime, beyond this temperature, above this temperature, right, then you will not see any boundary between the liquid and the gas. And this supercritical fluids, they're technologically very important, right? So the thing is, the density of the fluid varies, okay, as you vary the temperature, the density varies, and as the density varies, the solubility of certain solutes also varies, right? So what you could do is, for example, carbon dioxide is a very common supercritical fluid. Okay. I think 31 degrees Celsius is the critical temperature for that, and about 73 atmospheres is the critical pressure. Okay. You also need a pressure, right? If you are at that high temperature, you also need certain amount of pressure before the gas can be liquefied. So that is critical pressure. So if you are with supercritical carbon dioxide, you could actually use it. In fact, at some of the more expensive dry cleaners, they use supercritical carbon dioxide to remove the dirt out of your clothes. So it can dissolve all the organic material when it is in the supercritical state, but it does not dissolve when it is a liquid or a gas. Okay, or rather, what you would normally do is you would then release the pressure, right? You take out the supercritical fluid, the organic impurities come out with it, and then you either you increase the you reduce the temperature, or you reduce the pressure, and then everything would immediately turn over to the gaseous phase. So what you get is, it's clean, like carbon dioxide will escape, and you'll be left with all the dirty material over there. So that is one thing. So exactly the same kind of technological application also is used for example, for extracting caffeine from coffee. Nowadays you get decaffeinated coffee. So that's the way you do it, because that thing is soluble in supercritical carbon dioxide. So you can actually remove it. Or for purification then. So you can remove a lot of things which are soluble in this supercritical carbon dioxide, and if your compound is not soluble. So it's used a lot in the pharmaceutical industry. So these kind of applications are there, right? But dry cleaning is of course not a very common application, but still it is there. So technologically very important, these things. Water has a supercritical temperature of 300 and wait, let me just see if I have written it down. Yeah, 374 degrees Celsius, and the pressure required is 218 atmosphere. So that's huge. I mean, critical temperature. Did I mention supercritical? Okay, critical temperature. Anything above that is supercritical. Okay. If all the temperatures above critical are supercritical. Right? Huh?
Sir, above critical temperature and pressure is a
It's a supercritical fluid. You can't say it's a liquid or a gas. Right?
Sir, the temperature scale is in Celsius.
This one is in Kelvin.
So the graph cannot be like
Huh?
graph. You can't have temperature.
Right, that's why I put it over there. So it's almost down to zero. Why I put it over there was because we do have a critical temperature over here for the liquids and gases, but there's a clear distinct boundary between solids and gases. Okay? That's why I put that over there. Okay. Now, there's another important point over there, the intersection of the three curves. Okay. And that intersection of the three curves over here is known as the triple point. Temperature triple point. Okay. You could have, I mean, different. We've already seen this. The triple point of water, we've already seen. That was used to define the Kelvin scale, right? So one was the zero of the temperature scale. The other one was triple point of water. Now, what's so special about triple points? All three phases coexist. So, what's so special about it then? Huh? Right. There's only one temperature and pressure at which this can happen. Remember, the earlier temperature scales were based on boiling point of water or melting point of water at 1 atmosphere. But the atmospheric conditions can change, right? And then your boiling points would change, or your melting points would change. Melting points not so much, but boiling points definitely more. So this triple point is what we say invariant. Okay, the values for water, of course, are, in case of water, the triple point is 273.16 Kelvin, and I think it was 611, yeah, 611 Pascal. So 10,000 Pascal is 1 bar. Okay, so this is a fraction, 1/100th of an atmosphere roughly. Okay. So it's a very low pressure for the triple point of water. But if we are at this temperature and water, this temperature and pressure, then water exists in all the three phases. It's in equilibrium with all liquid, solid, and gas. All of these three are in equilibrium. And this is invariant, means I cannot have another triple point of water. Right? So it's the perfect thing to choose if you want to define a standard. Right? Like we saw, when we saw the law of corresponding states, that was the perfect thing to, the critical temperature was the, and the critical pressure and the critical volume, because they were internal to the gas. Right? So likewise, triple point is also invariant. And why is it invariant? It's invariant because mathematically you would see that three lines meet, right? And we have two variables over there. Okay. So it's a simultaneous solution of these three equations with two variables. So I can have only one value possible. Right? You could even think of the gaseous phase, for example. If I want to remain in the gaseous phase, how many degrees of freedom do I have? Degrees of freedom means how many variables can I change at will? I can vary two variables. I can vary the temperature and I can vary the pressure. Right? I'll remain in this gaseous region. Yeah, of course, I cannot vary the pressure too high. Okay. So I'll remain still in the gaseous region. If I want in the liquid state, again I have 2 degrees of freedom. Solid, 2 degrees of freedom. If I want to be on one of these lines describing, for example, the solid liquid transition, how many variables can I change? Only one. Right? If I define the pressure, for example, as 1 atmosphere, then I know what is the boiling point of water. If I change the pressure, I do not have any control over this boiling point now. Sorry, melting point. Solid liquid is what we are talking. So I do not have any change over the melting point. Right? It's fixed. So degree of freedom is 1. There's a general formula which will not derive, but you can have a look at. The derivation is given in Atkins also. We'll just tell you over here. F is equal to C minus P plus 2, where F is the degrees of freedom, C is components, P is phases. We'll come to components later. For the moment, we are just dealing with a single component system. Okay. I think for today's lecture, we'll stick to single component systems. So a component, for example, is water. Water is one single component. If it's a mixture of salt and water, then we have two components. Phase. Now, the definition of phase is very important. Over here, it's very clear. Gaseous phase, we have one phase. Liquid phase, solid phase. In each case, we have just one single phase. But on the lines, there is a coexistence of two phases, or it's biphasic, I would say. On the dot, that is the triple point, there are three phases that coexist together. And if I use this formula, then 1 plus 2. So for a single component system, this just reduces to 3 minus P. And if all the three phases coexist, then I do not have any degrees of freedom, as we've already seen. Right? If I want two phases to coexist, then I have only 1 degree of freedom. And if only one phase, then I have 2 degrees of freedom. Also, mathematically, I can even prove that 4 phases cannot coexist together. I'll leave it to you. If you want, you can read the proof. How many variables can I change at will? How many parameters can I change at will?
every substance has a triple point?
Not necessarily. Not necessarily. For example, there is that also has a triple point, but it's not between solid, liquid, gas. The example that I'm telling you. This is helium. Okay, and helium has two liquid phases. Okay. This is the only known example which has two liquid phases, other than liquid crystal. Okay, so just liquid phases. So one of them is the normal liquid helium, and the other one is called the superfluid, which means its viscosity is 0. So it can flow without any hindrance. So this is, and these two liquid phases are set. The solid phase is on top of this, right? So it's found at a much higher pressure, and then below that you have both the liquid phases, and then below that you have the gaseous phase of helium. So that is one example which does not have a triple point in this sense, that solid, liquid, and gas coexist.
So the line between liquid and gas, on that line we have liquid and gas coexist.
Coexist.
So, but if we take a beaker with some liquid, it has its vapor pressure.
Yes.
So liquid and gas are coexisting.
Yes.
So that's not always a
No, that is not.
So then how
It's an open system. One thing, the pressure is not the pressure of the vapor. Okay, it's the external pressure, which is the pressure of the vapor plus the pressure of the atmosphere. So if you want to actually calculate that, we can do it, right? And we can actually say how much vapor would come out of it, right?
Let's do it. Let's do it.
Okay. It's not a problem. Yes. Huh? Because you want to know exactly what all you can control when you want to do any processes, right? Okay. So this is the kind of phase diagram that is common for most of the substances. Okay. Carbon dioxide, for example. We just mentioned that. Now, there are some values for carbon dioxide which I don't know if I have over here. Okay. I don't remember correctly, but I think the triple point for carbon dioxide is somewhere around 5 atmospheres. Okay. Which means my normal melting point, right? I don't have a normal melting point in case of carbon dioxide. So let's just draw that for you. So let's say this is the triple point, and that's 5 atmospheres. That's pressure in atmospheres, temperature in Kelvin, right? So that's your solid, that's liquid, that's gas. So 1 atmosphere is somewhere over there. Huh? Wherever. So always what happens is that the solid gets converted into a gas. And that's why carbon dioxide, solid carbon dioxide is known as dry ice. It does not melt under normal conditions. At 1 atmosphere, it does not melt. And that's why it's very useful for a lot of purposes, refrigerant and all the. Nowadays, all these ice cream carts, they have their own electrical supply, but earlier they used to put bricks of dry ice into the carts.
Yeah, according to this, at 1 atmosphere it should be solid carbon dioxide.
Depends on the temperature. Whatever, at 1 atmosphere, what will happen is, depending on the temperature, it will have a solid to gas phase transition. Okay. Water, on the other hand, has a slightly different kind of a phase diagram. This is fine, this is fine, but the solid liquid transition has a slight negative slope. Oh, it's a straight line then. It's a very slight negative slope. Maybe I can just show you the proper diagrams if you give me a moment. So this should be chapter 4. Okay, that's for carbon dioxide. So the triple point is 5.11 atmosphere. And that's 216.8 Kelvin. And the critical point is 304, which was roughly 31.1 degrees C. It was 72.9 atmosphere. Okay. And the slope, if you see, so dP by dt is positive. Right? Because there is, I mean, that's what you expect normally. If you increase the pressure, then the temperature, the melting temperature goes down. Goes up, sorry. Goes up. Yes. That must be the sublimation point, I guess. There's written TV. You'll have to hold them. Responsible for that. That's what the phase diagram of water looks more like. So at what we normally see, what I have normally drawn over there, is just this solid. This is one form of ice. There's 17 various forms of water that are known. So yeah, and this one shows 11. Yeah. But there are 17 various forms which are known, and every pure water. So, but it depends on, this is the normal form of ice that you know. Okay, that's just gas, and that's the liquid water. Now, if I look at one of those forms of water, you can see that these are very high, exist at very high pressures. So all these forms you can not find in normal daily life, daily circumstances. But for example, glaciers, they're huge things with heavy masses. They can develop such large pressures. In fact, people even feel, or people have actually reported these things, that some of the movement of glaciers might be attributed to some of these forms of ice. Okay. But normally what you find is the type 1, which is the normalized liquid and vapor. And you see, I said that the slope is negative over here. It's very slightly negative. In fact, you won't even realize it. It's almost straight.
Now I think this also has the phase diagram of helium.
So in the normal sense of solid, liquid, gas, it does not have it. The triple point is between the superfluid, the normal liquid, and the gas. The solid exists at a much higher pressure.
So what is the significance of that negative slope?
Yeah, we were coming to that.
So we have three phases at another point: solid, liquid, and superfluid. So is it different that triple point will be with gas or something? We could have taken that as triple point also.
Yeah. Wouldn't matter. I mean, all I wanted to say was this is not between the solid, liquid, gas.
Now, you ask me what is the significance of
The negative slope over there. Right? Normally, if you are compressing something, you are trying to bring the molecules closer. Okay? Which means expansion would require more energy. If I am compressing something and I am bringing it more closer, and at the same time melting normally means expanding. It will require more energy. More energy means I'll need to put in higher temperatures for it to melt. But in case of water, if I'm compressing it, I'm actually taking it more towards the liquid state. Liquid water is more dense than solid ice. So I'm making its melting process easier in that form.
we could do a thermodynamic analysis over here, and for that what we would require is to go back to the concept of the Gibbs free energy. And for a single component system, we can say that the molar Gibbs free energy is equal to the chemical potential mu.
It has more significance when we come to multi-component systems, but for the moment we'll start introducing this concept of the chemical potential. And the idea is that this always, so dG has to be less than 0 for a spontaneous process, right? Is equal to 0 when it's in equilibrium. If it's greater than 0, then the reverse process is spontaneous. Yeah, this is well understood. Huh? Right. So, essentially, the idea is that the chemical potential must go to a lower value if I want the process to be spontaneous. Right. So we'll start developing these ideas. So for spontaneous processes, the chemical potential must go to a minimal value possible. Now, we've already seen one of those things where I think I had plotted G as a function of temperature. Right?
Yeah, del G by del T at constant pressure was equal to minus S, right? Or I could even switch over to chemical potential, say del mu by del T at constant pressure is equal to minus S molar.
Once we are talking about the chemical potential, everything is a molar quantity. It's very interesting to see that this chemical potential actually is like a potential. So it drives to a lower potential, right? Everything. So if you're sitting on top of a hill, things prefer to roll down to the bottom of the hill. So this is more, that's your gravitational potential. This is more like chemical potential. Okay, so tries to come down towards a lower potential. And what we had seen over here was, if I plot, and then we had for the gas, liquid, solid, right? And whichever had a lower chemical, instead of G, then let me just plot mu. So by the time I really need it, I'll get used to mu. So whichever mu is lower, right, that particular state would be favored. That was the simple idea over there. And because we know that the entropy of gas is large, and that's why this slope is large, entropy of a solid is the smallest, so this slope is the smallest. This is minus of entropy. Okay, now I could even think about these two curves over here at a particular pressure, right? So I could plot mu as a function of temperature at a particular pressure. Okay. So let's say this is a low pressure. And we are talking of melting. So this would be the solid and that would be the liquid, right? Now what's the change in the Gibbs free or the chemical potential or the Gibbs free energy? One and the same thing for the moment. What is the change as a function of pressure? So del mu by del P at a given temperature. V, or in this case V molar. Right. In general, the molar volume of a solid is smaller compared to the molar volume of a liquid. Right. So the change in mu at a particular temperature would be large for a liquid and small for a solid. Yes? The change is just equal to the molar volume. So if I were to take this up, it would be small for a solid, right? Small for a solid and large for a liquid. Something of that sort. Just exaggerate it a bit. Don't bother too much about it. Right? Actually, I exaggerated it a bit too much. So now I cannot actually show you that the change of a liquid is from here to here, and the change of a solid is from here to here at a given temperature, right? I just talked about. That's the way I would plot, right? So if that kind of a thing happens, then normally this was my melting temperature at the lower pressure, and this would be my melting temperature at the higher pressure. Right. So since you asked it, we can actually prove it over here, that why the temperature should increase, why this slope of the solid liquid line is actually positive for most substances. But in case of water and any other associated liquid for that matter, the molar volume of the liquid is smaller. Water is most dense at 4 degrees C, right? So in that case, what would happen if I were to draw the same thing again?
So that is the one at low pressure. Now the change in the solid is much larger. Oh, sorry. Change in the solid is much larger, and the change in the liquid is much smaller. Right? And let's see where our temperatures are. So low pressure, high pressure. Yes. So this is still mu, this is still temperature.
Yes? And that's the significance of a slight negative slope that we have in case of the phase diagram of water.
Yes?
Look, what I have plotted was the slope which is equal to the entropy, right? Okay, there's one small assumption. The entropy does not change much over this small temperature range. And that's why I plotted parallel lines. Okay. So this is the slope for the liquid, this is the slope for the solid. Right? Del mu by del T, that is the negative of entropy of the solid, this is the negative of entropy of the liquid. Okay. Now, how does mu change with pressure? So at a higher pressure, so del mu by del Pt is just nothing but the molar volume. Okay. So if I hold the temperature constant at some point, and I want to see the molar volume, and if the molar volume of the liquid is larger than the solid, then we get such a situation. If in case the molar volume of solid is larger, then the change in case of solid would be larger, right? I could just hold the temperature at one place and see this is the change, right?
At any one point, I can see this is the change. At any one point, I can see this is the change, right? And then I could see at all different temperatures and plot this.
So how does that answer the question that del P by dP by dt should be negative for that graph? Why is that slope negative?
What else do you want?
So I should put on into temperature.
I increase the pressure, the melting temperature drops.
Let me plug this just one moment before it switches on.
Now we would actually like to see some more quantitative features of the phase diagram, right?
And to do that, we would prefer to concentrate on something like the change of pressure with respect to temperature, and how we can correlate this with the thermodynamic quantities that we have at hand. Okay, so in general what we have over here is, let's say we have pressure, we have temperature, and we have some
transition. Okay.
So let's say we have a phase alpha over here, and we have a phase beta over here, which could be solid, liquid, solid, gas, liquid, gas, or for that matter any other phase. And what I wish to inquire is that if I know what is the transition temperature at this particular pressure, if I know that, can I predict what is the transition temperature at a different pressure? Yes? Yes, you already know the equations? Provided we know the equations. So let's develop those equations then. Now, the idea is that, if you remember, melting is one of these transitions. Boiling is another transition, which we've come across till now. So all of these transitions are essentially happening in equilibrium, right? If they're happening in equilibrium, that means the Gibbs free energy does not change, right? At equilibrium, delta G is 0, which means that the chemical potentials of the two phases must be identical at equilibrium, right? So all I can write over here is that mu of alpha at a given pressure and temperature is equal to mu of beta at the same pressure and temperature. Okay. And if I slightly change this mu so that I still lie on this line, if I slightly change the pressure and temperature to another value, T prime and T prime, let's say, at that point also mu of alpha would be equal to mu of beta, as long as I am on this line. Then, if that is true, then I can also say that the change in the chemical potential d mu alpha is equal to d mu beta, right? So if I change it from P to P plus delta P and P plus delta T, still the chemical potentials of alpha at P plus delta P, T plus delta T is equal to the chemical potential of beta at P plus delta P, T plus delta T, right? So if both the points are same, I'll say that the change is also the same. And it's an infinitesimal change. So d mu alpha is equal to d mu beta. That's what I write. And I already have my fundamental equation, one of the fundamental equations, which tells me what d mu alpha and d mu beta is. Right? Minus of S dt plus V dt. So what I can write is minus of S. Now, because we are dealing with the chemical potential, we'll use molar of alpha dt plus V molar of alpha dp would be equal to minus S molar of beta dt plus V molar of beta dp. So if I say that beta is the second one, so I am going from alpha to beta, let's say that way, okay, then the change during the transition would be minus S molar alpha plus S molar beta into dt is equal to V molar beta minus V molar alpha into dp, or I could write this, because this is beta minus alpha, the first term, S molar, the entropy of beta minus entropy of the phase alpha. So I could write this as delta S of transition times dt is equal to delta V of transition times dp, and now we have the equation, right?
So you could have derived this directly from those partial derivatives by applying that minus one cycle equal to minus.
But it's important to tell you that the chemical potential is equal, right?
So otherwise I cannot derive it. So what we have then is simply dp by dt is equal to delta S of transition by delta V of transition, right? Ah. Right. We have.
So if ever it's required, then you should remember that it's at a constant chemical potential,
Right. This particular equation goes by the name of Clapeyron equation.
and since when a transition is occurring, for example boiling or melting is occurring, then delta S of the transition is nothing but delta H by T, right?
As we've already seen that. So I could even write this dp by dt is equal to delta H transition by T times delta V transition. If I can write like that, let's examine the three different
Transitions that you see: solid to liquid, liquid to gas, and solid to gas.
let's have a look at how we can actually quantitatively define these transitions. So we go to the solid liquid phase transition. Now I could so I already have dp by dt is equal to delta H by T delta V transition. So I could change this transition to fusion. Now in general,
Delta H fusion is always a positive. It's always a positive number. Delta V fusion is normally a positive number. It's a very small positive number, normally. In case of water, it's a negative number. It's again a small negative number. So you have the slope of dp by dt is huge because there's a very small number in the denominator, right? So that's why whenever you're seeing these slopes which I showed you, all of them are almost straight, slightly bent in the positive direction or very slightly bent in the negative direction, right?
so you could actually evaluate these things, that we could say, okay, dp is equal to delta H fusion by delta V fusion dt by T, and then integrate. So I wanted to start with some pressure P star and go to a pressure P. So T star likewise under temperature T.
I can assume delta H and delta V to be independent of the transition temperature for a small change. Doesn't matter.
So if I integrate this, all I get is just I get P minus P star would be equal to delta H fusion by delta V fusion log of T by T star, right? And remember, what we were looking for was a very small change between this green and red dot. We're looking for very small changes. So if the change in pressure or temperature is small, or rather at least one of them I could assume to be small. Let's assume the temperature to be small, right? If the slope is large, then and the temperature is small, the pressure could be large. Right? So if the temperature is small, then this particular log T by T star I can actually write as log of 1 plus T minus T star by T star. So I can write like this, and then this fellow is a very small number because T and T star are close by. So it's like log of 1 plus x is equal to 1 x plus x minus, and all the square cube terms I can just dump off because it's a very small number. So I could just write just straight away as P is equal to P star plus delta H fusion by delta V fusion into T minus T star by T. Right, and T star is the temperature where I started. Okay, so and T is whatever temperature I am going to. So this is more like a straight line equation, right? So remember, if for whatever you've seen till now, for example, the more general one over here, this is more of a straight line. These two are a bit curved. So that explains why this solid liquid transition is more like a straight line equation. Okay, we could do the same analysis for a liquid gas transition. Okay, so in case of the liquid gas transition, what I can assume is that one, whenever it's going from into the gaseous state, then the entire volume is maximum that of a gas. So I can ignore the volume of liquid. That's one thing. A. Ignore volume of liquid. So delta V transition is nothing but it's equal to the volume of the gas. So volume of the gas. The other thing is that if for some reason I can assume that it's an ideal gas, which is quite good for low pressures at least. And remember, we are already in the high temperature regime when we are talking of liquid gas transitions. If I could assume that ideal gas, right? So then my Clapeyron equation becomes dp dt is equal to delta H. Oh, now this is liquid gas, so this boiling, right? Vaporization, okay. By T, and then we have delta V, which is now V of gas, which is RT by P. Yes? So what I get is T square R P, or I can take the P on the other side since we already have P, so that's dP by P. So d log P by dt is equal to delta H by RT square. That fellow has a name to it, it's the Clapeyron equation.
So we are considering it to be an ideal gas. So how can it be liquid? It can exist in liquid.
No. Sorry. It's not the liquid that is the ideal gas. First, I considered that the change in volume is because everything has changed into gas, and I ignore the volume of the liquid. And when it has changed into gas, I say, okay, let this be ideal gas.
But if it would have been ideal gas, so it.
Okay. I get your point. Then it couldn't have been liquefied. Right. Fair enough.
So this calculation is just an approximation.
It's an approximation. Very true. And you'll see that it's a decent enough approximation. Okay. So that way, of course, we cannot consider anything to be ideal gas because nothing goes up to 0 frequency.
Always that is an approximation. Okay. So for the liquid gas, we have then, let's just quickly integrate this, or maybe I could leave it for you to integrate. Maybe I'll just tell you the final result over here, which I have. So if I start with a value of P star and go to P, we'll be integrating between these limits. P star to P is equal to delta H vaporization by R dt by T square. It's not a complicated integral anyway, but what we get out of it is more interesting. What we get is P is equal to P star into e to the power minus chi, where chi is defined as delta H of vaporization by R 1 by T minus 1 by T star.
So, essentially, that's an exponential growth with temperature. Right? Growth. I mean, if you just integrate this and put it, you'll get this value. I put the minus sign. Okay, that's why I said it's a growth. The same would be true in the case of sublimation. Solid going to gas. Again, I can assume that delta V is just because of the gas. So solid doesn't have any volume. And I could again use the ideal gas equation and come up. So instead of delta H vaporization, I would have delta H sublimation in that case. Again, that too would be an exponential growth.
And if I go back and show you the general form of these curves,
you realize that these are more like exponential growths. So that's what. So the Clapeyron equation and the approximate version of Clausius-Clapeyron equation. They help you to understand these phase diagrams more quantitatively, and you can actually relate to the heat of fusion or heat of vaporization or heat of sublimation, how the temperature varies as a function of pressure, or the pressure varies as a function of temperature. Right. Anything? Great.
So what is the proof of that straight line?
What is the?
So the theorem proves that solid to gas transition rate is exponential, and ceramic is also exponential.
Yeah, that is what. These are.
So when it is solid to liquid, there is a straight line.
It's a straight line.
What is the
Okay.
So that's a y is equal to mx plus c. Okay. To sum it up then, I will tell you about phase transitions. And phase transitions, I don't know if you've already heard these terms, first order phase transition, second order phase transition, maybe somewhere. But Paul Ehrenfest, one of the greatest physicists of 20th century, he gave this classification to start with. So what he called was, something was first order phase transition, something was second order, and we just discussed that.
So that is the Ehrenfest classification.
Okay. So we've seen, for example, liquid gas phase transition. All of the phase transitions which we've been talking about are first order phase transitions according to this classification. And what exactly defines a first order phase transition? What happens to the volume if I go from liquid to gas? It increases. So what I would do is,
I could plot volume as a function of temperature, and let's say that's by transition temperature. Okay, so the volume, if I heat something, the volume increases normally. Yes, we'll not worry about the special case of water. Well, anyway, for boiling it doesn't matter. So if I heat something, the volume increases, and if it goes over to the gaseous phase, suddenly the volume increases, right? It goes something like that.
there's kind of a jump. There's a discontinuity, right?
I could say molar volume if you prefer that, which is nothing but del mu by del P.
Right?
I could think of
almost parallel, sir. But you made some.
I think I gave it a larger slope than it deserved. Sure. The slope has to be lower if I'm
Talking of a transition from,
maybe I could expand it properly so it doesn't leave you any doubts. Okay.
what would happen to the
Enthalpy. temperature. We'll just vary. So I just plotted temperature for all these graphs over here. I just said, okay, everything we are varying with temperature. There's a delta H of transition, right? And it's always endothermic, right? Heat is being taken up. H increases. So, I mean, normally what we have considered is that for a liquid, for a gas, H is independent of temperature, although there is a slight variation. So we could just say that H changes slightly and then there is a jump. Okay. Yeah, don't bother about the slopes, which I'm not even thinking of. I should actually. Okay, so that's H. What about the chemical potential itself? All with respect to temperature. This is one thing which will be continuous because at the phase transition it's in equilibrium, right? But the slope of the liquid, that is the entropy of the liquid, is smaller than the entropy of the gas. So, and these are negative slopes as far as we remember. So that would go something like that and then something like that. Okay. What about entropy? Yeah, all with temperature. I need one more column, so I'll just erase this. Entropy with temperature. The entropy of gas is larger than the entropy of a liquid, and as we heat, the entropy increases. So, naturally, something of that sort. What are the thermodynamic quantities were we interested in? We could calculate everything starting from any of the thermodynamic quantities. You can count. With G, it's mostly H, what you want, right? Cp, right? Cp, the heat capacity. The heat capacity generally is given by, well, that's the lower temperature limit, but it increases with temperature. It becomes more and more difficult to raise the temperature when you go to larger temperatures. So, well, there's a slight increase, but what happens at the transition temperature? What is the heat capacity at a transition temperature? It's infinite. Because all the heat that goes into the system does not raise the temperature, but it causes the transformation. So it's something like, let's say, some slope over here, infinite, maybe some other slope over there. No, it's infinite. It's not an infinite, so it's not continuous. Right. So if we go back to so what we see over here is that all the first derivatives of
the chemical potential are discontinuous.
So mu is continuous, whereas del mu by del z, whatever that property is discontinuous. Remember, H also I could relate to mu. G plus Ts or mu plus Ts.
So, huh? So in this case of in this kind of a transition, what we have is mu is continuous, although the slopes are different, but the first derivative of mu, the first derivative of the Gibbs free energy or the chemical potential is discontinuous. All these are first derivatives, right?
Yes.
No, with respect to temperature or pressure, right? Volume is with respect to pressure. H is again with respect to temperature, because I could define this as mu plus Ts, and S is equal to minus del G by del T at constant T. This is with respect to temperature. Cp? Cp is equal to Cp by T is del S by del T, right? And del S is del G by del T. So that is the second derivative. Well, I'll tell you about that once I come to the second order phase transition.
The first graph is P versus P.
All are with respect to the temperature.
Yeah, maybe I just write there temperature, 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 temperature. Huh?
There's a phase transition. Whenever there is a phase transition, the two phases are at equilibrium with each other. If they are at equilibrium, dg is 0. Chemical potential is nothing but the Gibbs free energy, molar Gibbs free energy for a single component system. So it could be T or P. That's what we have seen, right?
This classification is only for single component systems.
Not really.
Then we can equate G.
For the moment, just treat it for single component systems, right? First order phase transition.
So this is the first order phase transition. It can be extended, okay? So this is what we call as first order phase transitions. Okay.
I don't know why he called it first order. Okay. That's the name given to it. Maybe just because that's. See, if there is a transition, you want to see some discontinuity, and that's in the first derivative. Because the second order phase transition has a discontinuity in the second derivative.
Okay. Then we have something called a second order phase transition,
Which is not something which is commonly seen every day. I mean, I could tell you one example. For example, we have a tetragonal system. Okay. Now, a tetragonal system is one crystal structure which has A and B sides equal, but the C side is longer. And then because one of the edges is longer, there is an asymmetrical nature of this distribution. So if I start applying pressure, then the C-axis would get compressed more. Okay. Let's say we have something which has this property. So the C-axis gets compressed more, and then at some point of time, what you get is a cube where A, B and C are equal. And now there is no more anisotropy left in the system. So now if I am applying pressure, it will be equal on all the three sides. So it will continue to get compressed along all the three directions. It will remain to be a cube. Right? As long as one of the directions was elongated, there was anisotropy, and this could be compressed to a larger extent. So now what would happen to the volume of such a system during the phase transition? So the volume decreases, becomes a cube, and further decreases. But there is no discontinuity in the volume. Right? So if I were to plot that,
for example, the volume decreases, right? It might decrease at a different rate. I don't know what rate.
okay, but there is no discontinuity in the volume. Yes?
Likewise,
There is no discontinuity in the enthalpy. There is no discontinuity in the entropy of the system. Okay. In fact, the chemical potential also does not change any slopes because there is no discontinuity in the entropy. Right. So the slope of the chemical potential would be a straight line. It would not change.
but the heat capacities,
That would change. Okay. Because the two systems are different systems. The tetragonal one and the cubic one, they would have different heat capacities.
so that would be a discontinuity over there, right? So what we have in this second order, sorry, I must mark this. So that the first derivative of mu is continuous. Second derivative is discontinuous. So the heat capacity would have a discontinuity over there. Huh?
Yes. The graph should be oh yeah, thanks.
Thanks.
I mean, in this case it's pressure, but there are lots more examples where it should be temperature. But yeah, you're right. In this case it was definitely pressure. Right. I was talking of compression in this particular transformation of tetragonal system to a cubic one. Thanks.
Okay. So we can stop here.